So before watching this lecture, you should know about the linear regression model and what we mean by the model being nonlinear in data and nonlinear in parameters. So this lecture is about a very popular model in econometrics called the log-log model, or sometimes it's called the log-linear model. But the foundation of this model is the power function. So if you remember, the power function is a function that looks like this. It has a constant multiplied by x, and that's raised to another constant. And let's focus on the case where x is greater than or equal to 0, so that we can allow a and b to take any values that we like. This is a pretty nice function because it can capture a lot of different types of behavior. So, for example, it can be a linear function. For b equal to 1, it's just a linear function like this, in which case a is simply the slope of this function. So if this is a equal to 1, then you can also have b equal 1 and a equal to 2. For b greater than 1, it has this shape. It's always x on this axis and y here, or y is just the value of the function. So this could be, for example, b equal to 2. And the higher the b is, the more convex this function is. So this is perhaps b equal to 3. For b in between 0 and 1, the function looks like this. So this could be b equal to, well, I can draw that a little bit better. b equal to 1/2. For a equal to 1, this is just square root of x. And for negative values of b, the function looks like this. This perhaps b equal to -1. So a lot of different types of relationships can be captured by the power function. And the idea here is just to let our data determine which of these best capture the relationship between y and x. So if I have a random sample of yi and xi, then I can postulate a relationship between them in the following way. I can say that the expected value of yi given xi is a power function, and then I use, instead of a and b, we switch to beta 1 and beta 2, so xi to the beta 2. And then I just say that beta 1 and beta 2 are unknown parameters, and I will use the data to estimate these. So I will use the data to try and find the best fit for my model. Now if I want to use this model, then we typically have the case that yi is greater than or equal to 0 and xi is greater than or equal to 0 for all I. And that is simply to avoid, for example, if beta 2 is 1/2, we want to avoid taking the square root of negative values. And if xi is greater than or equal to 0, then yi will be greater than or equal to 0. Well, at least the expected value will. But this is, of course, still not a statistical model because we need some randomness as well. And for these types of power functions, it is actually common to use a multiplicative error instead of an additive error. So our complete model would be yi is equal to beta 1 xi raised to beta 2, and not plus epsilon I, the way we typically do it in a regression model, but multiplied by epsilon I, where epsilon I is now a random term that's also assumed to be greater than or equal to 0. So this will be our complete specification. So notice in this model, yi is equal to the expected value of yi multiplied by epsilon I. Or if you like, the epsilon I is now not the difference between observed and expected value of y, but the ratio of them, like this. Now, since this is a model where we have a multiplicative error term, this is not in the form that we have written the regression model. Not even the regression model that was nonlinear in parameters. So that means that we really have not considered any kind of methods of estimating these parameters. But the thing is that we can easily make it into a regression model by simply taking the log of both sides. So I'll just remind you of some of the log rules. If you take log of a product, it's the sum of the logs. That works also if you have the log of a product of 3 terms. So log of a times b times c is log of a plus log of b plus log of c. And the second log term we need is log of a raised to b. Then this b goes in front, so it's b times log of a. If we use these rules, take log of yi, then I need to take log of this side here. That's a product of 3 terms, this term, and this term. So I can just take the log of each term and add them. So it's log of beta 1 plus log of xi raised to the beta 2 plus log of epsilon I. And finally, I can use my second log rule to move this in front. So this is log beta 1 plus beta 2 log xi plus log epsilon I. So still this doesn't really look like a regression model, but it will pretty soon. If I just rename log of beta 1 to beta 1 prime, so beta 1 prime is now just defined as log of beta 1, log of the constant that's in front of the power function. And I do the same thing. Epsilon I is an error term that can only take positive values. So taking a log of it is okay. This will simply be a new error term that we call epsilon I transpose. So put this all together, we have log of yi equal to beta 1 prime plus beta 2 log of xi plus epsilon I prime. This is now a linear regression model. It is not linear in data, but that's okay. We can still use OLS to estimate it. It is, however, linear in parameters. There is just one tiny issue here that you can raise, and that is the fact that we are actually estimating beta 1 prime and not log beta 1. If I had kept log beta 1, then it would be nonlinear in parameters as well. So in this model, I'm actually not estimating beta 1. I am estimating beta 1 prime. But that's typically okay because in regression analysis, we in general don't care very much about the intercept. The emphasis is typically on this parameter, beta 2, and that has not been transformed. That's the same beta 2 as we started with here in our model. So as you can see, all I need to do to estimate this model that I started with is to log my y data, log my x data, and then do a linear regression model using my logged data. This is the reason it's called a log-log model, because I end up doing a regression of log y on log x. Also, our assumptions must be made in terms of this transformed error term. So we have to assume that the explanatory variables are exogenous, and that is then with respect to these error terms. So the expected value of epsilon I prime conditionally on xi must be 0. That kind of makes sense if you think about it, since the original error terms were defined as this ratio, then the original error terms ought to have an expected value of about 1. Yi is on average the same as the expected value of yi, so this ratio is on average 1, and the log of 1 is 0, so epsilon I prime will be on average 0. The same goes for the homoscedasticity assumption. It must be made in terms of the epsilon I prime. Those are the guys that needs to be homoscedastic. So this was for the case where we had just one explanatory variable. So let's generalize this to an arbitrary number and state the results. So the log-log model then starts with the following. The expected value of yi given xi. Say, for example, the expected level of production in a firm given xi, which is all the factors of production, might be described using this Cobb-Douglas production function, for example. Or we could have the expected demand conditionally on some factors such as price, income, and so on, to be given by this function. Very common and very popular form specification for the conditional expectation. To this we add we add a multiplicative error term. So we don't write plus epsilon I, but we write multiplied by epsilon I. That kind of makes sense because all the other terms are multiplied by each other, so it makes sense that everything else that affects yi in addition to the explanatory variables should be multiplied to this expression. And that in turn means that the error term must be defined as the ratio of yi to the expected value of yi. So that if we multiply both sides by this expected value, we have the complete model like this. Not a regression model, but can be made into a regression model by logging both sides. So if we do that, take the log of both sides. We did this for just one explanatory variable, but the idea is the same. You'll get that the log of yi is the log of beta 1 plus the beta 2 comes in front, log of xi2 plus, and so on. And at the end you have log of the error term. Do the relabeling thing, call log beta 1 prime, and call log epsilon I prime, and we have a linear regression model. Not linear in data though. So let's have a look at how to estimate the parameters of this log-log model in Gretel and eViews. So it's pretty straightforward. We can use OLS, ordinary least squares. So let's say I want to do the model where final is my y variable and SATV, SATM, and the GPA are my x variables. So if I want to do it as a log-log model, I have to create log of these variables first. So let's just do L final as, and we do that as log of final. Log is the natural logarithm in Gretel, so that's the one we want. Then we do the same with the other ones. Like this, so I have log the final, SATM, SATV, and the GPA. So all I have to do now is just run a regression on the logged values. Like this, and this is the result of my log model. Keep in mind that this is not an estimate of beta 1. It's an estimate of log beta 1. But these are direct estimates of beta 2, beta 3, and beta 4. So next, let's see how to interpret these numbers, these estimates. Because this is a model that's nonlinear in data, we cannot interpret these numbers as marginal effects. They do not answer the question, what happens to y when x increases by 1 unit? We'll see that they actually answer a very similar question, namely, what will be the percentage change in y when x increases by 1%? Well, approximately that at least. So let's try to figure out why this tells us that when SATM increases by 1%, the result on the final score increases by approximately 0.8%. That is why we need to use percent and not units when we work with the log-log model. First, just a quick review on elasticities. So let's say I have y as a function of x, and this function is some constant x to the a, where x is greater than or equal to 0. And this is generic notation now, so this y and x doesn't necessarily have anything to do with the regression model. Well, we know that the percentage increase in a variable, so the percentage change in y is given by the change in y, so y new minus y old divided by what we start with. That's the percentage change, and you need to multiply that by 100 if you want it expressed in percentages. So if you start with, let's say 100, you go to 103, then you get 3 over 100 or 0.03 or 3%. We can use the delta notation to simplify this a little bit. So we write this as delta y over y, where delta y is the change in y, the new one minus the old one, and y is the starting value. Similarly, the percentage change in x is given by the same thing, delta x over x. So if we look at the ratio of these two, the percentage change in y over the percentage change in x, we see that that's equal to delta y over y divided by delta x over x. So if y increases by, say, 4% and x increases by 2%, then this number would be 2. The increase in y is twice the increase in x if we measure it in percentage. Now we can simplify this expression and write it as delta y over delta x times x over y. This part here, that's the thing we typically call a Newton quotient. We know that as delta x goes to 0, this converges to the derivative f prime x. So that means that this is approximately equal to dy dx times x over y. And this approximation is better the smaller delta x is. And the expression is called the elasticity of y with respect to x. Here is the derivative of y with respect to x. The whole thing is the elasticity of y with respect to x. The derivative tells us approximately how much y increases in units when x increases by 1 unit. If you post multiply that by x over y and you have the elasticity, then it tells you instead approximately how many percent y increases if x increases by 1%. So units, percent. So let's figure out what the elasticity is for this function. If f of x is cx to the a, it's easy to find the derivative. That's just c times differentiating a power function. The exponent goes in front and we decrease it by 1 unit. So that's the derivative. That's dy dx. So the elasticity is then equal to dy dx, c times a times x to the a minus 1, multiplied by x divided by y. And y is this whole thing, x to the a. X to the a minus 1 times x, we can put a little 1 here. Remember, we just add the exponent, so this product is just x to the a. So this will cancel with this c will cancel with this, and it's just a. So we can see that this exponent is indeed the elasticity. If a is, for example, 0.5, it means that when x increases by 1%, y will increase by 0.5% approximately. If a is minus 2, then x increases by 1%, y will decrease by 2% approximately, and so on. So going back to our model, where yi is beta 1 xi to the beta 2 times epsilon I, and we have this conditional expectation of y given x. Let's drop the subscript, generic observation, then this is beta 1 x raised to beta 2. So this is like my f of x function in the above exercise, and this is like my y in the above exercise. So beta 2 will be the elasticity, and it's given by the derivative of this y variable with respect to x times x over this y variable. So this is exactly what beta is with no approximations, and we know that this expression on the right hand side is indeed the approximate increase in y in percentage when x increased by 1%. There is also an alternative expression for this beta, which is often really useful. If we go back to our non-econometrics notation, a x to the, well, actually I did c x to the a, and this is my y, then I can log both sides. So log y is equal to log c plus a times log x. And this gives us another interpretation of y, of this elasticity. We can view the elasticity simply as the derivative of log y with respect to log x. So the elasticity, also another way of saying it, measures how much the log of y increases when the log of x increases by 1 unit, approximately. And we know that this change is again approximately equal to the percentage increase in y when x increases by 1%. For the econometrics model, we interpret this beta 2 as the derivative of log expected value of y conditional on x with respect to the logarithm of x. So this is an alternative expression for beta 2 or the elasticity. So here's the generalization for the case where we have more than one explanatory variable. The interpretation of the beta parameters is as follows. Beta j, where j is now any number from 2 to k, not the beta 1, can be viewed as the derivative of log expectation with respect to log xj, or as the derivative of the expectation with respect to xj times xj over the expected value of y given x. No matter how you write it, it's still approximated by the percentage increase in y when x increases by 1%, keeping the other explanatory variables constant. So we can see, for example, in this result that the biggest effect on the final result, if you can increase one of your previous results by 1%, you will get by increasing the SAT math score. If that's increased by 1%, the increase in the score is almost 1%.